Under the determination of order of reaction, we have two methods that we can learn from. Number one would be initial rate methods, which has inspection and substitution method. We have beautifully done up examples with perfect work solution. Some of it is printed at the end of the lecture notes for you to refer to. You should be able to attempt initial rates question at this point. Now let's look at the focus of this video, the graphical method. Graphical method is actually very, very simple to execute once you have the graph. So we're going to look through the different types of graph that can allow us to determine the order of reaction. First, we will look through concentration time graph, and then we'll look through the other types of rates versus concentration or rates versus concentration square graph. All of us should have the basic understanding of what to expect, really, because most of the time the shape of the graph or certain characteristics of the graph already tell you the order of reaction with respect to that reactant. So let's look through it together. As we have a reaction between A and B to produce C, we can have rate equation as such. We then will have to go on to develop procedure in order to obtain data for the graphical analysis. Basically, we need to execute experiment that allow us to collect data, to plot a graph that allow us to determine the order of reaction. If I were to find out the order of reaction with respect to A, I would need to create a situation where B is no longer influencing the rate. As such, I will actually have B be in large excess. So if you record earlier a portion of the lecture, you will know that when B is in excess, then the concentration of B will remain approximately the same throughout the experiment, and therefore concentration of B term become a constant, and therefore it will be subsumed under the constant K and then give you a K prime. If you do not know this part of mathematical reasoning, you may want to check your lecture notes and videos again. Now, determine the concentration of the reactant or product at various times might be necessary for us to plot this particular concentration time graph, because I need to know the concentration across a period of time, right? So then we will deploy different and various experimental technique to allow us to get this kind of information. And then at the end of the day, we'll be looking at plotting this data point and then having this concentration time graph develop. So very important things that we must know, and before we further look at how we can determine the order, we must remember that the reactant B is in excess to ensure the concentration of B remain approximately constant during the course of the entire reaction, such that B initial concentration of B term becomes a constant number, and therefore we can focus on solely the impact of A on the rate of reaction. Now, this example of mine only has reactant A and B. So that's why we only, if I keep B constant, then I can investigate A. But in the unfortunate event, if I have like three molecules reacting together, three chemical reacting together, then I will need to make the other two in large excess so that I can look at one of them. Okay, that's quite simple, easily understood, right? Overall order of the reaction is the order of reaction with respect to A in this case. Really, because I make the order of reaction with respect to B become pseudo zero order. By putting it in large excess, I have a pseudo zero order with respect to B, and therefore the overall order of the reaction that I am able to observe through experiment will be solely respected to A, and therefore reflecting the value of M. So this part, I hope everyone is clear. So the first thing that, the first scenario that we might see when we plot a concentration time graph is that, okay, we get a straight line. It's a good news, because if you get a concentration of reactant versus time graph in a straight line form, it is a clear sign that it is a zero order with respect to A, meaning the rate of reaction is independent on the concentration of A. So if you want to find a K value, the K value of your rate equation will be negative of the gradient of this particular straight line. So as I mentioned also in the earlier portion that we have recorded, if concentration of reactant time graph, you get a straight line like this, you are looking at a zero order. with respect to the reactant that you're investigating. Now, what if my concentration time graph is a curve? It is normal because the reactant is used up over time. The reaction is definitely not a zero order. So linear graph show that it's zero order. Non-linear graph only say that it is not zero. So we have uh, other possible options open. But it can be first and it can be second, and we don't know yet. So then we will then move on to determine half-life to find out whether it is first order or not. Now, if successive half-lives is constant, that means you find the time for it to halve and find the time for it to halve again, and the time is the same, approximately the same number, then we can then conclude that it is a first order with respect to A. Okay, now sometimes, especially if the graph is plotted by ourselves, then there will be some deviation. So if your time is slight small difference, like our first t half was 7 minutes and second t half was 6.5 minutes, that's totally okay. We can say that it's approximately constant, which is why on my slide I didn't say exactly equals to constant, but like approximately constant will be fine. After all, we are looking at experimental data. Sometimes deviation or slight difference is actually expected. Okay, concentration versus time graph being a curve, but successive half-life is not a constant. Then at this point, you can choose to plot 1 over concentration of the reactant versus time graph. If you end up with a straight line graph, then the reactant is indeed second order with respect to A. So this is one way to handle it. If after we check the half-life, but unfortunately it is not constant, then this is one way for us to confirm whether it is second order or not. Now, this is a gentle reminder to all of us. In our H2 syllabus, we are familiarizing with zero, first and second order, but in reality, there are a lot more other options. It doesn't have to be a whole number, it doesn't even have to be a positive number. So it doesn't have to be 0, 1, or 2 in reality. Just that in your syllabus, we are mostly dealing with these three. Okay, now let's look at this particular example we have right now. We have a CH3COCH3, a ketone, reacting with iodine to give you our CH3COCH2I, H plus, and an I minus. So there are two reactants here, the CH3COCH3 as well as the I2. We use a calorimeter to monitor the concentration of I2. Why? Because I2 aqueous is actually colored species. If you have higher concentration of I2, then you will have higher intensity of the color, and the calorimeter will be able to read the signal. So as you can see, because I2 is a reactant, the concentration decreases, then the calorimeter will give us the signal accordingly. And if we do the scanning over time, we'll be able to monitor the concentration of I2 by using the machine itself. All right, so if we look at the question itself, it's quite interesting, right? Graph A is plotted with the condition of 0.1 mole per dm cube of H plus, slope MA. Graph B is 0.2 mole per dm cube of H plus, slope is MB, and MB is equals to 2 times that of MA. Okay. So what is the order of reaction with respect to iodine and hydrogen ion? Considering this, either graph A or graph B, we are having a strict line. What the strict line means, we just talked about this, right? If a concentration time graph is a straight line, we are getting a zero order. So check your y-axis in this case. Your y-axis is actually corresponding to concentration of I2. So logically, you will be able to tell me that the order of reaction with respect to I2 is zero order. Is that okay? Okay, so make sure that you take a moment to think through. You're able to apply this. So, what is the order on of reaction with respect to hydrogen ion? If we look at the two graph, you can see that graph B, the concentration of H plus ion is actually double. When the concentration double, the slope is double. the slope actually represents the rate of reaction, right? So rate of reaction is double when H plus is double. That allows you to immediately conclude it is actually first order with respect to H plus. This is an interesting example that we have carefully selected for you, really because we can conclude both order of reaction with respect to I2 and with respect to H plus, sorry, using this straight line graph. So first thing first, you need to check whether you have already recognized that concentration time graph straight line means a zero order to whatever the corresponding to the y-axis label. And this is the interesting first exposure that we can actually manipulate the concentration of the other reactant and allow you to make a deduction from there. Given that the reaction is first order with respect to propanone, write the rate equation for the reaction. So over here, we have propanone, we have I2, we also have H plus. Propanone is first order, I2 is zero order, H plus is first order. Obviously, the rate equation has to look like this. I don't think you struggle with this. What are the units of the rate constant? Okay, so let's think through. How do I get to mole minus 1 dm3 s minus 1? Very importantly, we recognize that all the concentration is mole per dm cube. Time given is actually seconds on the graph. Can you highlight the label of the x-axis? Then you should be able to work this out. We have gone through details on how to come up with the unit for rate constant. If you struggle with this one, you might want to check with your tutor face to face instead of trying to solve it on your own.